In this episode, we will talk about MiniMax Speech, Intrinsic Zero-Shot text-to-speech with a Learnable Speaker Encoder. And, think about how often we interact with synthesized voices these days.
Oh, absolutely. They're everywhere.
Right. From virtual assistants answering our questions to audiobooks bringing stories to life. The technology behind it all, text-to-speech or TTS, has just made incredible leaps recently.
It really has. What's particularly exciting, I think, are these things called codec-based models.
Okay, codec-based.
Yeah, you can sort of imagine them as these super sophisticated audio processors. They're trained on, well, huge libraries of speech.
Huge amounts of data.
Exactly. And now they can take a tiny snippet of someone's voice, maybe just a few seconds.
Oh.
And from that, generate remarkably realistic speech. It's truly a transformative time for the field. This ability, creating high-quality speech from minimal input, it's not just cool tech.
Right, it's practical.
It's unlocking totally new possibilities. Think how much more natural our interactions with AI could be.
Or just creating audio content faster.
Precisely. And right at the forefront of all this is the idea of voice cloning.
Which brings us to something called zero-shot voice cloning. Now, you might have heard zero-shot when people talk about large language models, LLMs, where a model does something it wasn't specifically trained for, just based on, instructions. MiniMax Speech is doing something similar, but for voices.
That's a great way to put it, yeah. In the context of MiniMax Speech, zero-shot voice cloning means the model can synthesize speech in a specific person's voice using just a short audio clip as reference.
Okay.
And crucially, it does this without needing any text alongside that audio and without any specific fine-tuning for that speaker beforehand.
So it just hears the voice and gets it.
It's almost like it has this built-in understanding of what makes a voice unique, the timbre, the quality, and it can apply that to new text.
Now, it's important to contrast that because previous ways of doing this, especially with what they call autoregressive TTS models.
At our models, yeah.
Right, these models that generate speech bit by bit. They often needed both the audio and a transcript of that audio to clone a voice.
That's right.
And that could cause problems, couldn't it? Like if the transcript wasn't perfect or the model couldn't speak for very long coherently.
Exactly. That's a really good point. Those earlier AR models, while pretty powerful for their time, could definitely run into issues if the text prompt didn't perfectly match the audio sample's acoustics.
Mismatches.
Yeah, mismatches. And also that step-by-step generation could sometimes lead to the quality kind of degrading over longer sentences. MiniMax Speech tackles these problems head-on, really, with a key architectural change: integrating a learnable speaker encoder right inside its AR framework.
Okay, so this learnable speaker encoder sounds like the secret sauce.
It's definitely a huge part of it.
So our goal in this deep dive is really to unpack how MiniMax Speech, with this encoder and its other tricks, gets such high-quality voice cloning from so little input. Let's maybe start with the overall architecture. It's described as an autoregressive transformer-based TTS model. So for maybe someone listening who isn't deep into AI, the transformer part, think of that as a really smart system for understanding connections in sequences, like words in a sentence, or here, the sounds in speech.
Good analogy. It's great at context.
And autoregressive, like we said, means it builds the speech piece by piece based on what it just made, like painting, adding strokes.
Exactly. The transformer architecture is especially good at grabbing that context and understanding long-range dependencies in the input text. That's vital for getting speech that sounds natural, the rhythm, the intonation, what we call prosody.
Okay.
Now, the really innovative part, as we mentioned, is this learnable speaker encoder. Think of it like a highly trained ear.
Okay.
It listens to a reference audio clip and pulls out the unique defining bits of that speaker's voice, their timbre, the texture, the resonance.
The sound.
The sound, precisely. And crucially, it does this without needing to know what words are being said. It's just analyzing the voice's sonic fingerprint.
So it's ignoring the words, just listening to the acoustic properties.
Yeah.
And the learnable part is key here, right? It means it's not just grabbing some off-the-shelf model.
Exactly right. Many older approaches used pre-trained speaker encoders, often borrowed from systems built for speaker verification, or SV.
Like just identifying who is speaking.
Yeah. The problem is the data used to train those SV models and their main goal, just verification, might not be perfectly suited for the specific needs of actually generating high-quality synthetic speech.
Different jobs.
Totally different jobs. MiniMax Speech's encoder, though, is trained together with the main AR model. It's end-to-end optimization.
Ah, okay.
This lets it learn and extract exactly the speaker features that are most helpful for synthesizing speech in that specific voice. It's custom built for the TTS task.
That makes a lot more sense. Like training a violinist specifically for violin, not trying to get a trumpet player to do it.
Perfect analogy.
Now, the research says this model makes expressive speech, captures the voice's unique traits, all in a zero-shot way. But it also supports one-shot voice cloning with even higher similarity. What's the difference they're drawing there?
Yeah, they're very specific about this distinction. They call it intrinsic zero-shot versus one-shot.
Okay.
So intrinsic zero-shot is what we've mostly been describing. Give the model some reference audio, say 10 seconds of someone talking, then give it some text.
Right.
The model speaks that text in the voice it learned only from that 10-second audio. It hasn't seen that voice paired with that text before, no fine-tuning.
Got it. Just learns the voice from the sound.
Yeah.
So what's one shot then?
One shot, in their definition, means you provide that same reference audio, but you also give it one paired example.
An example?
Yeah, like a short audio clip of the target speaker saying a specific sentence and the text for that sentence. It's like saying, here's the voice and here's an example of them saying this phrase.
I see. So it gets a bit more information.
Exactly. And it's worth pointing out, many other models, often called zero-shot, actually rely on this kind of text audio prompt. MiniMax Speech's big step is doing high-quality cloning with just the audio reference, hence intrinsic zero-shot.
So the advantage of that true text-free zero-shot is pretty significant then. No need to transcribe the reference audio, which could be messy.
Absolutely. You bypass that whole transcription step. Plus, it lets the model focus purely on the acoustic signature of the voice, separate from what was actually being said in that reference clip. It's capturing the raw sound.
And that leads to better prosody, you said.
Yes, potentially richer prosodic variation. Because it's not anchored to the rhythm and intonation of one specific text audio prompt, it has more freedom to generate natural-sounding prosody that fits the new text it's synthesizing.
That makes sense.
Plus, because that learnable speaker encoder is designed to grab language-agnostic features, the core voice qualities that exist across languages, it makes cross-lingual synthesis more robust. You know, clone an English voice, have it speak Mandarin, but still sound like the original speaker.
That's impressive.
And fundamentally, having this strong, disentangled speaker representation builds a great foundation for extending the model to do other cool things.
Okay, so besides the encoder, the research also brings up something called Flow VAE, another key piece for boosting the audio quality. Can you break that down?
Right, Flow VAE. It's a pretty clever technique they developed, integrating a flow-based generative model with a variational autoencoder, or VAE.
Okay, VAE, I've heard of those. They compress data, right?
Essentially, yes. In audio, an encoder-decoder system learns to take speech, squash it down into a compact representation, the latent space, and then rebuild the audio from that compressed version.
Right.
Now, traditional VAEs often assume this latent space follows a nice, simple mathematical pattern, a standard normal distribution. It's convenient, but maybe too simple for complex speech data.
Like forcing all voices into one simple box.
Kind of, yeah. Flow VAE improves on this. A flow model uses a series of mathematical operations transformations that are perfectly reversible.
Okay.
It uses these transformations to learn the actual, often messy, complex probability distribution of the data. In Flow VAE, they apply this flow model to the output of the VAE's encoder,
So they take the VAE's compressed version.
which might still be a bit complex statistically, and use the flow model's transformations to map it neatly onto that standard normal distribution.
Why is mapping it to that standard normal distribution helpful? What's the gain?
Well, by making the encoder's output conform, via the flow model, to that standard normal pattern, they argue it actually boosts the encoder's ability to capture information. It pushes it to learn more meaningful, disentangled features from the audio.
Interesting.
And they also found that training the encoder and the neural vocoder, that's the part that turns the latent code back into audible sound waves.
Got it.
Training them together in this Flow VAE setup leads to much lower error when reconstructing the waveform compared to older methods using MEL spectrograms.
MEL spectrograms. Those are common, right?
Yeah.
But they lose some detail.
They're very common, yes, but they are a transformation that can discard some finer acoustic details. This joint training on the waveform seems to preserve more fidelity.
So Flow VAE helps create a better, more detailed, compressed version of the audio, leading to better sounding speech in the end. And this whole system, the latent flow matching model with Flow VAE, it also uses the voice fingerprint from the speaker encoder.
Exactly. To really nail the speaker's identity and boost quality, that global timbre information from the speaker encoder, which works on Mel spectrograms of the reference audio, remember?
Right.
That gets fed into the flow matching model, too. They also mention sometimes using a tiny bit of the beginning of the sentence being generated as an extra prompt during training.
Ah, okay.
This whole design allows the model to work in both pure zero-shot mode, just reference audio, and one-shot mode, reference audio plus a text audio sample, when it's actually generating speech. Gives you options.
It definitely sounds like a complex but well thought out system. And the paper backs this up with some pretty strong results, right? Let's talk about the objective tests on voice cloning. They use things like word error rate, WER, which basically measures how accurate the spoken words are compared to the text, lower is better, and speaker similarity, SIM, which measures how close the voice sounds to the target. They tested this on a dataset called Seed TTS Evol. What did they find?
Yeah, the results on CDTTS Evil, which has both Chinese and English speech, were really quite impressive. MiniMax Speech got significantly lower WER scores, meaning fewer pronunciation errors in both zero-shot and one-shot modes, compared to strong baselines like CDTTS itself and Cozy Voice 2.
Lower errors, clearer speech.
Exactly. And in some cases, the WER for MiniMax Speech was actually better than the original human ground truth audio.
Wow, better than the human. How?
Well, cleaner pronunciation, potentially fewer hesitations or slight imperfections than might exist even in carefully recorded human speech. It indicates really exceptional clarity.
What about that interesting finding where zero-shot WER was sometimes even better than one-shot WER? That seems counterintuitive.
It does seem a bit odd at first glance, yeah. The researchers suggest that in the pure zero-shot case, the model relies only on the raw acoustic properties from the reference. It's not influenced by the specific rhythm or intonation of a one-shot prompt example.
Okay.
This might give it more freedom to find the most natural prosody for the new text, which could actually improve overall intelligibility and lower the WER. The one-shot prompt might subtly bias the prosody in a way that isn't optimal for the new sentence, even if it helps similarity.
Fascinating trade-off. And the speaker similarity scores. Did it sound like the right person?
It really did. In zero-shot cloning, the SIM score was remarkably close to the ground truth audio. That's huge validation for the Learnable Speaker Encoder. It's capturing the voice identity effectively just from the audio.
And a one-shot.
In one shot, the SIM scores actually beat the ground truth and Cozy Voice 2, and were right up there with CTTS. So that extra text audio prompt can push the similarity even higher, maybe giving finer details about speaking style.
So, solid objective results. But how did it sound to actual humans?
They did subjective tests too, right? Ended up top of the Artificial Arena TTS leaderboard. That sounds big.
It's very significant, yes. Getting the top spot on that leaderboard, especially since all their entries use the Intrinsic Zero-Shot cloning, is a massive vote of confidence from human listeners.
And that leaderboard compares models from lots of big players.
Oh, yeah. The ELO scores, which come from people choosing which voice they prefer in a head-to-head comparisons, showed listeners preferred MiniMax Speech over top models from places like OpenAI and 11 Labs, specifically for naturalness and expressiveness.
And it beat models from Google, Microsoft, Amazon too, by a good margin. By a substantial margin based on those ELO scores, yeah. And again, the key thing the paper stresses is that this top-tier quality came from voices cloned purely using the zero-shot method. It really shows the model's power to generalize and sound human without needing tons of data for each speaker.
That really feels like a next step for the field.
It absolutely does. Achieving that level of naturalness zero-shot, beating models potentially trained on hours per speaker, it speaks volumes about the architecture.
Now, the model supports 32 languages, which is pretty amazing. How did it do in the multilingual tests? They checked 24 of those languages against 11 Labs multilingual V2.
Right. Overall, the word error rate performance was comparable to 11 Labs. But when you dig deeper, MiniMax Speech did significantly better in languages with complex tones or lots of distinct sounds.
Like which one?
Think Chinese, Cantonese, Thai, Vietnamese, Japanese. In those, MiniMax Speech had a clear edge in WER. 11 Labs had more errors.
Okay.
But maybe even more importantly, MiniMax Speech had markedly better speaker similarity scores across all 24 languages they tested.
So it kept the speaker's voice identity consistent, no matter the language.
Much more consistently, yes. That language-agnostic speaker encoder seems to really pay off there.
And that ability to separate voice from language leads to cross-lingual synthesis, right? Taking a voice from one language, making it speak another. How did that go?
They specifically tested cloning Chinese speakers and having them speak other languages. The results showed that the intrinsic zero-shot method gave significantly lower or better intelligibility than their own one-shot method in these cross-lingual cases.
So zero-shot was clearer across languages.
Much clearer, yes. Interestingly, one-shot sometimes got slightly higher similarity scores cross-lingually, but the pronunciation was so much worse, higher were, that zero-shot was clearly the better overall approach for cross-lingual synthesis.
Makes sense. Clarity is paramount. They also did ablation studies, removing parts to see what happens. They looked closely at the Learnable Speaker Encoder versus using pre-trained embeddings or just a one-shot prompt. What did that show?
That ablation study really hammered home the value of the Learnable encoder. It gave the best balance between low whir and high sim.
Okay.
Using pre-trained speaker embeddings hurt the clarity higher whir, even if the similarity was okay. And the only prompt one-shot method actually got the best whir in that specific comparison.
Better clarity with just the prompt.
In that specific setup, yes. It suggests the prompt helps pronunciation, but it massively sacrificed speaker similarity. The voice didn't sound as much like the target.
So the Learnable encoder hit the sweet spot.
Exactly. Especially in one-shot mode, with the prompt, it offered the best trade-off. And its strong zero-shot performance further highlights its benefits. They also noted something crucial. The reference audio for the encoder must be different from the target audio being synthesized.
Why that?
To avoid what they call semantic leakage. If you use the same audio, the model might accidentally learn the content of the reference, not just the voice, which messes up synthesizing new text.
Ah, got it. Keep them separate. Finally, they looked closer at Flow VAE versus a standard VAE, both for just reconstructing audio and for the full TTS pipeline.
And Flow VAE clearly came out on top. In the resynthesis tests, just reconstructing audio, Flow VAE beat the standard VAE significantly on basically every quality and similarity metric they used. Things like PESC, STOI, similarity scores.
Okay, better reconstruction.
Ah.
And in full TTS.
In the full TTS synthesis tests, models using the Flow VAE latents generally got better or comparable WHERE and SIM scores compared to those using VAE latents. And importantly, listeners subjectively found the audio more stable with Flow VAE. Fewer weird artifacts.
So it seems every piece of this MiniMax Speech puzzle, the Learnable encoder, the Flow VAE, really pulls its weight.
Definitely appears that way.
Now, the paper didn't stop there. They explored some really cool extensions building on this core model. Let's talk about a motion control using LoRa low-rank adaptation.
Right. Since the AR transformer handles prosody, pitch, duration, the stuff that carries emotion, they looked at using LoRa for fine-grained emotional control. LoRa is this efficient way to fine-tune huge models.
How does it work for emotion?
You basically train small, separate LoRa modules for different discrete emotions, happy, sad, angry, etc., using emotionally labeled speech data. Then, when you want to generate speech with a specific emotion, you just plug in the right LoRa module.
That sounds neat. Efficient. Did the type of reference audio matter when training these LoRa modules?
It did, actually. They found that using neutral or even random emotion reference audio during LoRa training worked better than using references that already had the target emotion.
Really? Why?
Well, neutral references might have provided a clearer contrast for the model to learn the target emotion, leading to more expressiveness. And random emotion references seem to help create natural-sounding speech while keeping the speaker identity stable, maybe helping disentangle voice from emotion.
Interesting finding.
They also used multiple emotional examples for the same text to make sure the emotion wasn't just tied to specific words. And a big plus, this LoRa approach doesn't mess with the main MiniMax speech model, so it keeps its great voice cloning ability.
Very cool. They also looked at text-to-voice, T2V.
Yeah.
Generating completely new voices just from descriptions. That sounds futuristic.
It really does. T2V tries to get around needing an audio sample for every voice. It aims to create new timbres from natural language descriptions, like deep male voice, slightly gravelly, plus some structured tags for things like speech rate, gender, pitch, volume.
How'd they do that?
They built a dataset linking speech with these descriptions and tags. Then they took the internal voice representations learned by MiniMax Speech, compressed them down using PCA principal component analysis to 128 dimensions.
Okay.
And then they trained a small model to map the text descriptions and tags to this compressed voice space. They even used random masking during training, hiding parts of the input to make it work better, even with incomplete descriptions. It really opens up creative avenues.
Designing voices with words. Amazing. And the last extension, Professional Voice Clone, PVC. This sounds like boosting the quality for specific speakers.
Exactly. PVC is for when you have more data for one speaker and want to get their voice perfect, maybe if they have a strong accent or unique quality. Instead of retraining the whole huge model, PVC focuses just on optimizing that speaker's specific voice embedding.
The internal representation.
Yes, the embedding that the speaker encoder usually generates. You freeze the main model and just fine-tune that small embedding vector using the extra data for that speaker.
And then use that fine-tuned embedding instead of the encoder output.
Precisely. At inference time, you swap in the optimized embedding for that speaker. It's much more efficient than full fine-tuning or even l'array across the whole model.
I do this just for hyperaccuracy.
Right. Basically, yes. Refining that specific speaker spot in the latent space can improve accuracy and naturalness, especially for voices that might be outliers. It's scalable because you're just tweaking one small vector per person. They even mentioned using it in education to personalize materials with a specific teacher's voice.
Very practical. Okay, this has been a fantastic deep dive.
Yeah.
To try and sum up, the key breakthroughs seem to be that learnable speaker encoder, enabling true zero-shot cloning without transcripts,
Crucial.
and the Flow VAE architecture, really pushing the audio quality and speaker similarity.
I think that captures it well. The model's objective scores, plus that top ranking on the PTS arena, even doing zero-shot against potentially heavily trained models, really shows the strength of this approach.
And the extensions of motion control, text-to-voice, professional cloning show how flexible and powerful this core technology is.
Absolutely. They've built a very strong foundation, and they hint at future work on even better control efficiency. So we can probably expect more advancements down the line.
Definitely. So as we wrap up, maybe something for you, our listener, to think about. What does truly zero-shot voice cloning and this growing ability to create and shape voices just from text mean for you? What new creative or communication avenues might this open up?
And alongside those possibilities.
Right. What ethical considerations do we need to keep in mind as this incredibly powerful technology continues to evolve and become more accessible? Definitely gives us a lot to chew on.